The integrity and stability of the huge floating power station received a severe and unscheduled test on the trip upriver. As it was being partially submerged to pass under a bridge at Baton Rouge, it was struck by a tornado. The power station comes through the encounter with one of nature's mightiest forces, undamaged. 4 days after leaving New Orleans, the prefabricated power plant arrives at the site. It is towed through a cut in the levee and maneuvered into place over the foundation slab. Once it is precisely aligned, the huge structure settles gently into place. The levee is resealed and all the water is pumped out of the site, while 220,000 tons of super-plasticized concrete is pumped into the enclosed spaces of the structure to help anchor it permanently. With the plant in place, the job of installing the remaining equipment is completed. The main components to be installed are the turbines and generators. The 8 generating units, built by Asea Brown Boveri in Sweden, are each 28 feet across, the largest such units ever built. The bulb turbines by Kverner Hydropower of Sweden feature an automatic control system for the variable pitch turbine blades to respond to changes in demand, head, and flow. Bulb-type generators were chosen because of their well-established reputation for reliability in European power plants, and for their efficiency in situations in which the water level differential is relatively slight, as it is in Vidalia. A 40-mile transmission line is constructed, and connections are made with shore-based utilities. And final tests are run to assure that the Sidney A. Murray hydroelectric station is ready to go online. Finally, it comes down to the day of formal dedication in August 1990. The people of Vidalia and a host of visitors turn out to acknowledge the power of an idea and the effort it took to turn a dream into reality. They come to dedicate the largest prefabricated power plant in the world and the first hydroelectric plant in Louisiana, which is about to take up the task of harnessing a small portion of one of the world's great rivers to light the homes and lighten the tasks of the people of Vidalia and the customers of Louisiana Power and Light. A safe, clean, endlessly renewable source of power for generations yet unborn is about to be tapped. Like all such dedications, it marks both an end and a beginning.
Ceremony for the Sidney A. Murray Hydroelectric Station. I want to thank all of you for joining us here on this very special occasion for us.
When Dominion Capital in 1987 joined Catalyst Energy in sponsoring the facility that we're commissioning today, we knew that it would qualify for a number of major superlatives. It was the largest hydro project to be undertaken in this country in many years, and it was the biggest of its kind in the world. It also represented major engineering and construction challenges for all the companies involved.
I was told by a reliable source this morning that about 13 years ago, Mr. Murray appeared in the Corps of Engineer office and told us about this idea that he had and this vision that he had for a hydroelectric plant. And I'm also told that the people in the Corps at that particular time thought perhaps, Mr. Murray, that you were a little bit crazy in what you were about to pursue. We in the Corps of Engineers salute you and all of the other partners in your project. You've done a magnificent job. You've got a project which you, your community, and the nation could be very proud of. And we in the Corps of Engineers wish you and the project and your partners much success.
We feel like really our role here today is, we would like for it to be anyway, to represent all the people who have in any way participated in building this magnificent project here. At last count, I think we had 16 foreign countries and 24 states. I would say keep going and don't give up. You keep dreaming your dreams and hoping your hope, because who knows, someday yours may come true too. Thank you all, and God bless. It's taken probably over 3,000 people to do this project. And not only that, it's taken over $500 million to do this project. And I'm not, this is no one-man show. To do this, it's taken all these people and all this effort and time. I'm a little humbled by that maybe, but it's been a task and it's something I've enjoyed. But I think uppermost in my mind now would be seeing the goal that I envisioned back when I started. That is a long-term stabilization of energy rates for Vidalia ratepayer. That's what I was trying to do, and I see this project as accomplishing that goal.
The power of an idea, as Thomas Edison so clearly saw, is the power of persistence, of unrelenting pursuit of a dream. It isn't the flash of inspiration that lights Vidalia. It is 15 years of faith in an idea and the hard work of more than 140,000 people from all across the world. And that is something worth reflecting upon, here at the river's edge, where darkness has given way to light.
On the Mississippi River in Louisiana, USA, is a small town called Vidalia. But although it is small in size, it has taken a giant step to control escalating power costs. 72 kilometers downstream of the town, the Mississippi and the Red Atchafalaya rivers run close together, but there is always a difference in the level between them of between 2.5 and 6 meters. In 1977, the mayor of Vidalia conceived the idea of utilizing this renewable, non-polluting, free source of energy. A Federal Energy Regulatory Commission, or FERC, license to develop the site was obtained in 1982, and the resulting power station has been built and named after the visionary mayor, the Sidney A. Murray Jr. Hydroelectric Station. Two Quana hydropower companies played a vital role in the completion of this unique and innovative project. The two companies, Quana Boving of the UK and Quana Turbine of Sweden, collaborated in this project, which incorporates some of the largest bulb turbines in the world and required extremely complex project engineering and management. A major consideration during the preparation of the specification by the Baton Rouge consulting engineers Forty and Tablada, working with Segrier of France, was maximizing the annual energy output and minimizing the construction time. The radical method chosen was to prefabricate the complete power plant in steel at a shipyard in New Orleans, whilst more than 200 miles upstream, the civil construction work was being carried out at the site. Once the prefabricated powerhouse structure was fabricated and fitted out, it would be launched into the river and towed to site. The world's largest prefabricated power station. To maximize the energy output from a channel of fixed width, the turbine design was optimized by carrying out extensive model tests at Quana Hydropower's laboratory in Sweden. This was a major consideration, as the electricity generated was to be sold at a profit. From curves of predicted performance, the final specification was selected, giving a speed of 52 RPM and a runner diameter of 8.2 meters. Instead of having the turbine drive the generator directly, a two-stage epicyclic step-up gear was introduced to allow the generator to run at 600 RPM and thus requiring a much smaller bulb diameter. This arrangement was based on Quana Hydropower's experience at the very successful Avesta Lillfors hydroelectric power station in Sweden. The order for a modular prefabricated power plant structure, PPS, was awarded in December 1986 to Avondale Shipyards of New Orleans by the main contractor for the project, Ibasco Constructors Incorporated of Kenner, Louisiana. At the same time, ABB of New Jersey were awarded the contract for the electromechanical plant, and they in turn awarded a contract to the Quana hydropower companies. The contract awarded to Quana was for the design of the waterways, bulb structures, the downstream gates, and the supply of the 8 bulb turbines, step-up gear units, bearings, together with supervision of installation and commissioning of supplied plant. This was a major logistical and engineering task requiring close coordination between Quana engineers and those of the other contractors and subcontractors. Arranging for the correct delivery times of the casting, forgings and machine work from the various suppliers, many of whom were located in Europe, to complement the construction schedule of the power plant modules at Avondale was a particular problem. As can be seen, the turbine runners and chambers were built simultaneously in Sweden and England to ensure that they were ready on time. Although the runners were finished and delivered on time, for various reasons they were not installed at the shipyard, but installed on site. Meanwhile, at the shipyard in New Orleans, manufacture and assembly was underway of the fixed guide vane structures and of the bulb units housing the generators and gearboxes. The PPS was assembled from 50 and 100-ton modules, with special tools being used for certain machining operations after assembly. The downstream gates, which are used for isolation and also for controlling the flow during stopping and starting a unit, were manufactured to designs by Quana Boving, who also supplied all the control equipment. Installation of the plant at the shipyard was carefully planned at the design stage and closely supervised by Kvana hydropower engineers. As far as possible, all items of plant and systems were installed, tested, and pre-commissioned in the shipyard, saving valuable time at site. Work at the shipyard was substantially complete by May 1989, and the PPS was christened amid traditional shipyard ceremony. On the 6th of June 1989, the PPS was launched for its first and only journey, 200 miles up the Mississippi to the power station site. The trip upriver was fairly uneventful, apart from about the halfway stage, where it had to pass under a low bridge and be ballasted using an internal ballasting system and then deballasted again. All this had been planned beforehand, but something that definitely hadn't been planned was when a tornado suddenly struck. But the PPS rode it out, and what could have been a disaster resulted in only superficial damage. When the PPS eventually reached the site, it was towed through a gap in the levee, turned through 90 degrees, and maneuvered into position. Then the levee was rebuilt, the area dewatered, and the PPS ballasted to lower it onto its foundations. The PPS was designed so that its mass, when filled with concrete, would be sufficient to anchor it in place. When this was done, it was secured and, where necessary, grouted to the foundation, buttresses, and draft tube structure. The runners were installed at site because it was convenient to coincide this work with the voids in the structure being filled with concrete. This involved removing the top half of the runner chamber to allow the installation of the hubs and the assembly of the blades. Kvana engineers supervised the installation of the turbine runners, all 8 of which were installed in just 3 months by running 2 shifts. At the same time, the hydraulic cylinders for the downstream gates were installed. Once installation was complete, the remaining pre-commissioning of equipment and systems was carried out prior to rotational tests. The first unit to be commissioned rotated on the 26th of April 1990 and was subjected to a comprehensive commissioning program that included synchronization and overspeed testing. Once the team of Kvana and ABB engineers had verified that the first unit was behaving exactly as predicted, the remaining units followed very rapidly. The average time from first rotation to commercial operation was an astonishing 10 days. This achievement was the result of very careful planning at all stages and of the skill and experience of the engineers at site. All 8 units had completed their 30-day reliability runs by mid-August 1990, only just over 3.5 years from the release of the contract in December 1986. The final step in the story is the dedication ceremony, which took place on the 22nd of September 1990. Kvana Hydropower is participating in major hydroelectrical projects requiring advanced and novel engineering solutions all over the world. And the Vidalia story is an example of one such enterprise now successfully completed.
In the world of the engineer, truth is measured in decimal places, and error is swiftly and harshly punished by the laws of physics. So engineers aren't comfortable with idle boasts and empty titles. The world standard in hydraulic engineering is not a boast. It is Sogrea's commitment to the highest degree of excellence, founded upon long and deep experience and the most sophisticated technology available.
Sogrea's staff of more than 300 engineers and technicians is supported by one of the world's leading hydraulic laboratories and most advanced computer systems, drawing upon more than a half-century of experience around the world. Sogrea has consulted on projects which have produced 25 million kilowatts of hydroelectric generating capacity, 50 million acres of irrigated land, and hundreds of port and coastal, urban and industrial projects in 125 countries. This global experience encompasses every aspect of hydraulic engineering and planning. Rarely does a Sogrea engineer encounter a challenge for which there is not a wealth of precedent upon which to draw. Given the complexity and impact of hydroelectric plant design and construction, any aspect of this broad experience may come into play. With Sogrea as your consulting engineer, you are assured that no element of the project will be overlooked or receive less than expert attention. The depth of Sogrea's experience permits us to innovate solutions which help control costs and reduce construction times. For example, Sogrea's leadership in the design of low-head dams on large rivers resulted in the construction of the world's first prefabricated power plant at the Greenup Dam in Kentucky on the Ohio River. The 72-megawatt project, using a maximum head of only 30 feet, was originally conceived as a conventional hydroelectric plant built on site. But plant and site considerations suggested to Sogrea engineers that it could be prefabricated, with all generating equipment installed, then floated into position, submerged and anchored in place, with significant reductions in construction time and cofferdam costs. While construction crews at Greenup were building the cofferdam and foundations, the plant itself was being built at the largest shipyard in France. Upon completion, it was loaded aboard a special ship for transport across the Atlantic. At the port of Baton Rouge, it was offloaded in two sections for the 2,000-mile journey up the Mississippi and Ohio rivers. The two sections of the power plant were towed into place, welded together into a single unit, then the cofferdam was dewatered. The unit was anchored by filling it with concrete. The weir was demolished and removed underwater. And just a little over 3 years after financing, the Greenup plant went online, a world record for such a project. Projects of this dimension are thoroughly tested prior to construction by Sogrea's design teams in one of the world's largest and most advanced hydraulic laboratories. The facility, located at Sogrea's headquarters complex at Grenoble in the French Alps, can test models of any complexity and extent for any aspect of a design. For the Greenup project, a comprehensive model of the locks and dams adjacent to the power plant was built to address concerns that the plant operations might affect the very critical flow conditions at the lock approaches, where huge barge tows navigate with only inches to spare. The model proved to the satisfaction of the U.S. Army Corps of Engineers that there would be no adverse effect. Sogrea's computer modeling capabilities are as sophisticated as its physical modeling. It can even perform the complex calculations necessary to simulate such hydraulic phenomena as sediment transport, current velocities and patterns, and transient flows. The worth of an innovation is measured by its suitability for replication and development. The Sidney A. Murray Jr. power plant on the Mississippi River near Vidalia, Louisiana, proved that prefabricated low-head power plants are a true and valuable innovation. The huge floating power station for the Vidalia installation was built at Avondale shipyards in New Orleans. The power plant houses 8 bulb-type turbines 323 inches in diameter, compared with 3 240-inch diameter turbines at Greenup. The 8 turbines provide a generating capacity of 192 megawatts, making it one of the largest low-head hydroelectric plants in the world. A further innovation was the speed increaser connecting the low-speed turbine to the generator, permitting the use of a less expensive generator. The power plant was built in 50 to 100-ton modules, each with its equipment in place. The 20,000-ton power station was launched in early summer 1989 for the 315-mile journey up the Mississippi to the site. The power plant was the largest single object ever towed up the river, towering more than 12 stories high. It had to be semi-submersible in order to clear bridges designed to accommodate ocean-going vessels. But though its construction and transportation upriver were a technological tour de force, the decision to make the Sidney A. Murray power plant the largest prefabricated hydroelectric plant in the world was driven by much more practical motivations. It was the most cost-effective way to build it. The search for efficient solutions and an open mind to the means of achieving them characterizes Sogrea. However, that should not be taken to suggest a penchant for risk-taking. On the contrary, the essence of good engineering is risk avoidance, and Sogrea's more than half-century tradition is one of meticulous adherence to the highest standards of engineering precision and excellence. Even if budget constraints demand a minimal approach, as they did in the Nangbito power plant on the Mono River in Africa, there is no departure from the highest standards. To reduce concrete costs on the project, a ski jump spillway was chosen. But to avoid downstream scouring, the precise design of the spillway and the shape of the downstream pool were meticulously developed in the Sogrea Hydraulics lab. When the spillway was opened, the design performed exactly as the laboratory model had predicted. Excellence, consistent excellence, is no accident. Sogrea maintains a highly experienced permanent staff of more than 300 engineers and technicians, with an average in-house experience of more than 15 years. This assures immediate access to top specialists in virtually all fields of water-related engineering, and a cross-pollination of experience and knowledge. Staff turnover at Sogrea is very small, so engineers assigned to Sogrea projects are well aware of the capabilities of their colleagues. This small turnover also assures continuity in the engineering staff over the duration of a project, which may span more than 10 years from feasibility study to completion. Sogrea's contribution to a project can be greatest when we are brought in at the earliest stages. Our great expertise and experience in dealing with regulatory agencies and international funding agencies like the World Bank make us highly skilled in feasibility and impact studies. At the implementation stage, Sogrea can conduct all geological, hydrological, and hydraulic studies, perform all computer and scale modeling,